Good evening, everybody. My name is Antonio Martinez. I'm a board member of the Peninsula Astronomical Society. And I'm glad all of you have come in today, both in person at the Los Altos Library as well as via the Zoom link. And so I wanted to welcome you all. First, maybe a few words from our VP.
Hi,
Maria.
I'm Maria. Welcome, like Antonio said, to our July meeting. So I'm the vice president of the Peninsula Astronomical Society, and we hold meetings like this about every 2 months. Is what we've been doing since coming back from the pandemic. And we also have a variety of events throughout the year. We host star parties and we do other things of that nature. I think there's twice a year International Observe the Moon Night that
and to the Peninsula Astronomical Society. My name is Francesco Meschia. I'm here to talk to you about narrowband astro imaging and how it can be used to take pictures of beautiful
place like this that is affected by the spotlight pollution. We're going to see how this is done and why it's being done. Why is it possible?
Why this can be done. So to begin with,
a few words about what astro imaging is.
Astro imaging is astrophotography. And the interesting thing about astrophotography is that it is almost
one of the very first
images that were taken with a photographic camera was actually the moon. I have here taken from Wikipedia 2 interesting images dating back to 1851, a total eclipse of the sun. And from 1883, the Great Orion Nebula. Of course, we're talking about black and white photography because it's the 1800s. But it was immediately astronomers recognized the potential for science of photography. And why is that? Well, photography can be used, first of all, to record stars and objects that are fainter than the eye can see, even through a telescope. Why is that? Because photography can integrate over time.
You can expose it 4 hours.
You can expose it 4 hours if you want.
Whereas the eye is essentially real time.
The eye is
It's very fast.
essentially a real time. It's not super sensitive.
Also interesting is that photography, if you
Interesting is that photography, if you record wavelengths that are not accessible to the eye. So we see everything from 400 nanometers of wavelength to about 700 nanometers of wavelength, goes from violet to red. But photography can record infrared radiation that we cannot see, and can record ultraviolet radiation that we cannot see either. So opens new domains to the astronomer. Also, photography can provide a record that is persistent. We still have in the archives of astronomical observatories glass plates with images taken at the very beginning of the 20th century. So it's lasting, and it can be shared, it can be printed in books, and can be sent to other people. So in more recent years, photography has proved to be an extremely powerful medium for the public communication of astronomy. Some of you may recognize the picture that I posted here from Wikipedia. It's an image published by NASA and the University of Arizona. It's called The Pillars of Creation. This image was very instrumental in popularizing what Hubble Space Telescope has done for astronomy, making accessible to the public a picture of an object that is, it inspires awe in the audience. It's, wow, this is incredible detail, and it's not only technological achievement to have sent up a telescope that can do this from orbit, but sends us back to Earth incredible pictures. On a much smaller scale, on the scale of amateur astronomers, if you wanted to do color imaging, you had to give up a lot in sensitivity. For amateurs, was replaced by electronic imaging. So we did like digital cameras. What happened in the realm of regular photography actually happened a few years earlier for astrophotography. Most interestingly, the use of electronic detectors opened the door for color imaging for amateurs. A green filter and one taking a blue filter, and when I combine them together, I produce a full color image, just like a television set can produce a full color image with the RGB filters. Even more recently, we're talking about digital imaging, so computers are a necessary evil in this scenario, but computer control of telescopes revolutionized image capture. It is now possible to take pictures in a fully automated fashion with your telescope in the backyard or with your telescope in the Atacama Desert in Chile, because everything is accessible via the internet, and the technology to do this has been mainstream for years now. In the same way, the processing of digital images has revolutionized what used to be darkroom work. You no longer needed to use anything chemical. Everything is done with the equivalent of Photoshop with a computer. And so the capabilities that we have today for astroimaging are leaps and bounds better than what was possible in the 80s when I personally started doing this. And to prove the point, I put here two on film. It was a film. And the one on the right, I took it in 2018 using the very same telescope that you see on the table. And it was taken with a regular DSLR camera attached to the telescope. So the level of detail that you can get, the level of depth, and of course the color is, in the 90s, I could never have imagined that we would have gotten here, to be honest. So now we have the technology, but what can we image? What can we take pictures of in the sky? Essentially of two types of things. In my opinion, is where the beauty is. You can find colors, shapes that trigger our pareidolia, and so we see pillars in that image, and not that attract our attention, essentially, and allow us to communicate the beauty of the night sky. And I have some pictures here to prove this. This was kindly offered to me by a colleague. So every that is all part of the dust and gases that exist between stars. And it comes in all sorts of shapes and forms. This is another, it's slightly zoomed in. It's another part of the Milky Way in the constellation Cepheus. There are areas that are of shapes that you can find, shapes and colors that you can find in various parts of the interstellar medium of the Milky Way, essentially. What we are looking at stars, actually way more than 7, of course, and they are still immersed in the cloud of they are in their own stellar nursery, if you want. Of the winter interstellar medium we can see is this, the so-called belt, Alnitak. It's mostly made of the hydrogen and also medium and the hot interstellar medium. Essentially a veil, a screen that sits between you and the outer universe. There is actually a portion of right of the dorsal fin of the shark. There is actually another that sits between us and the outer universe. At the very center of this picture is a galaxy at like 50 million light years away. And those wisps that you see is the interstellar medium of our own galaxy. So just a few thousand light years away, not millions. Then we have going up in temperature, we have the warm interstellar medium. Oh, something happened. Oh, thank you. So the warm interstellar medium is hotter than room temperature, so to speak, up to a few thousand degrees Kelvin. It is hot enough that hydrogen cannot form molecules. It's either atomic neutral hydrogen, means it has it's one proton and one electron, or it's ionized hydrogen, which the electron has been stripped away because of, for instance, energy received or thermal agitation. And of course, in addition to, it's not just purely hydrogen, there are all the other elements in trace amounts. The interesting thing is that ionized matter can glow, and in particular, hydrogen glows in visible light with a very distinctive red to purple glow. When we see a bright nebula in the sky through a telescope, or in a picture, that's typically warm interstellar medium. And I have some examples here. This is the Lobster Nebula on the left, the Cat Paw Nebula on the right. And that is the typical red color of, well, this is rendered in a certain palette, but the red information comes from the hydrogen present in interstellar medium. And you can see that this is actually a combination. Those are the various types of ISM, cold and warm and hot, may present themselves together. You see those dark clouds. Those are molecular clouds. So it's called interstellar medium, next to warm portions. Another example here is that shape on the right. It's called the lobster claw. And I want to show you that this interesting shapes replicate themselves at different scales. This picture here, if you look at here on the left, that's the lobster claw. This is a much wider field of view image. But as you can see, you can find a small nebula in the warm interstellar medium, or huge nebula like that big cloud, red cloud on the right. And then, of course, we have the hot interstellar medium with temperatures that typically exceed 1 million Kelvin degrees. And it's mostly gas that has been heated by a shock wave, or for instance, by a supernova, or this also happens in the coronas of stars, like our own sun, the corona of the sun, visible during total solar eclipses, like in the first slide that I showed you, has actually temperature that exceed 1 million degrees Kelvin, and mostly emits radiation in the X-ray domain, so we don't see it directly with our telescopes and our detectors, but can also has some portion in the visible spectrum. Now, with this introduction about the ISM, why did I do this? Well, because I want to talk to you about the challenge and the opportunities of imaging the ISM. The challenge is that apart from some famous objects like the Orion Nebula, the Eta Carina Nebula, the Lagoon Nebula, and a few others, most of the interstellar medium does not give off a lot of light. It's the nebula that you find are typically faint. So faint that it may be several times to entire orders of magnitudes fainter than the light that we have in the sky at night here in the Bay Area because of light pollution. So while we would always want to be in a place like this is Pinnacles National Park, and I was there to image broadband objects in the cold interstellar medium. Most of the time I'm not there, but my telescope sits in the backyard. And the problem with the backyard is that the neighborhood is like this. So the brightness of the background sky, it can be 20 or 30 times brighter than what we get from a Pinnacles National Park, which is already not a super dark place. If you want to see very dark places, you need to go in a desert like Death Valley in California, or in Nevada, or in Utah, or in the Atacama Desert in Chile if you are into the Southern Hemisphere. We are not that fortunate, but we can still do something about this, because a common misconception is that light pollution actually hides what you want to image. So the objects that you want to image are so faint, so much fainter than the light pollution that you cannot see behind it. Well, if you think about it, light always adds, right? It's the light from light pollution cannot cancel out the light from the stars or from a nebula. The faint object, like a galaxy that you want to image, always rides on top of the background. The problem is that is in the properties of light. So light is not a liquid flow. Light is formed of discrete particles that we call photons, and the photons arrive one by one. And the properties of the count of independent events, like photons that land on a detector of a telescope, or customers in a store, are described by a type of statistics that is called the Poisson statistics. Now, the Poisson statistic tells us that the actual count for each sampling of the same phenomenon will be spread around an expected value with a certain standard deviation. And the standard deviation is actually equal to the square root of the expected value. So if I have an object that sends me an average of 100 photons per second, and I expose for 1 second, I expose the first time, I have a 66% probability of getting 90 or 110 photons. And so I can get anything in between. There will always be a certain probability of reaching any non-zero count. What does this mean? It means that it's not the number of photons from light pollution that hides a faint object. It's the random pixel-to-pixel variations that make this weak signal undetectable, because the signal is actually smaller than the variations. This is what we call photon noise. It's completely random. It's due to the nature of light, and it cannot be removed because it's completely random. You cannot model it. It has nothing to do with the camera. You can have the best camera in the world and you still have a photon noise, because that's in the source, not in the destination. If you want to see an object, you need to be sure that its signal is larger than the associated noise. Otherwise, you're not going to be able to tell the signal from the noise. It's a problem of a signal to noise ratio. I have here a few examples. So it's probably not going to be very visible, at least not from my vantage point. But I drew on the right one brighter square in the middle of a slightly fainter rectangle. Now, let's assume that I illuminate this. This is like a piece of carbon, and I illuminate it with a faint light, and I take a picture of it. Let's assume that the background gives to my camera 1 photons per second in each pixel. And the signal, so the slightly brighter center of this image only adds 0.05 photons per second per pixel. So 1 photon every 20 seconds. If I expose it for a certain number of seconds, let's say 600 seconds, I'm going to have a mean value of my pixel of 600 photons in each pixel. And with the standard deviation, because of the Poisson statistics, of about 24 photons per pixel, which means that I have a good probability of, in any given pixel, having between 600 minus 24 to 600 plus 24 photons. The signal is only 30 photons per pixel, right? 0.05 times 600. So the signal to noise ratio is about 1. If I plot the pixel values, the number of photons counted by each of the pixels versus the pixel, you cannot really see where the object is, right? It seems random fluctuations. Now let's do the same exercise, but with a slightly brighter center. This slightly brighter, instead of sending me 0.05 photons per second, sends 0.08. So the signal to noise goes up, because the standard deviation is still 24 photons per second per pixel. Sorry, photons per pixel, but the signal is now 48 photons per pixel. So the signal to noise ratio is about 2. And you start to see that there may be something. You don't see the actual sharp edges, because the sharp edges are made smoother by the noise, but you can see that there is something. You are at the threshold of detection. If you image something even brighter, like this, in this case, we have a 0.2 photons per second per pixel. So it's still 5 times fainter than the background, the signal, but it's very well detectable. You can actually see the sharp edges. This is what we need to do if we want to take an image of the sky, of the objects in the sky. Sorry, too bad that we cannot crank up the brightness of an object that we'd like to image like I did in the previous slides. Of course, we could turn off light pollution by moving it to a dark site. And for certain types of object, that's all you can do. Or you can increase the exposure time or stack multiple images. When you do that, and if you have patience, you will find that the signal to noise ratio goes up like the square root of the total integration time, of the total exposure time. So I tried to put that in a hand-drawn graph on the right. You see that there are diminishing returns. If you have a decent signal with, let's say, 10 hours of exposure, the next step, so to speak, will be at 20. Sorry, not 20 hours. The following one will be at 40, and then 80. It quickly becomes impractical to push your exposure time too much. And sometimes we have to do it. The example that I give here, the background sky in Mountain View where I live is typically between 15 in a good night and 20 times brighter than at Pinnacles National Park. So what I can do in 1 hour from Pinnacles takes 20 hours from home. It's a sobering thought, but we can deploy some tricks to help us to even out the odds. With narrowband imaging. What is narrowband imaging? It's a set of techniques that involve capturing and processing later the images of astronomical objects using just a tiny portion of the electromagnetic spectrum as filtered out with the narrowband filter. I have some, those plastic boxes are the boxes in which filters are typically stored. How narrow is narrow? Well, the entire visible spectrum from violet to red is about 300 nanometers wide. So 400 nanometers correspond to violet, 700 nanometers correspond to red. When I image using full color filters, so each of the red, green, and blue filters has a bandwidth of about 100 nanometers. So 1/3 of the visible spectrum. When I image with a narrowband filter, my filters are about 4 nanometers of bandwidth. And there are filters that go as narrow as 3 nanometers. So they captured 1/100th of the entire visible spectrum. And why do we do that? Why would that be advantageous? Well, it is because, as we know from the 19th century, certain types of nebulae don't have a continuous spectrum, but only emit radiation in certain precise wavelengths. So this is a spectrum taken in a professional astronomical observatory of what's called the planetary nebula. So it is what's left after a red giant star has shed its outer layers. And you see that superimposed on a very faint continuum, there are some lines. Those are called spectral lines. And in particular, there is one strong line around the 6,500 angstroms, which corresponds to the alpha line of hydrogen, and a doublet of line around 5,000 angstroms, which corresponds to the doublet of the twice ionized oxygen, which we call oxygen 3. This nebula does not spread light in any other wavelength except for those. And this is incredibly advantageous for us because all of the warm interstellar medium, which is essentially a rarefied gas, but ionized gas, has a spectrum of the line type, as line emission, not black body spectrum. Black body is the type of radiation that you get from a star. It has a continuum of frequencies. Light is emitted only in discrete wavelength. And one example, why is so? So an example is here what would happen to an hydrogen atom in a cloud. So when the hydrogen atom is ionized, it means that the electron becomes free from the proton that is in the nucleus. This electron goes around, and this is almost, we are almost in a vacuum. At some point, we'll recombine with another proton to form an hydrogen atom. This electron will find itself initially at a higher energy state than the ground state of the hydrogen atom. And at a given time, will fall down to this ground state by transitioning to one or more intermediate states. When certain transitions, whenever there is a transition, a photon of light is emitted. Certain transitions, like from the third energy level to the second energy level, happens to be a photon of visible light, happens to be a red photon, it happens to be H alpha. And like H alpha, there is H beta in the blue region of the spectrum, and there are H gamma in the violet domain, and then the other lines are in the ultraviolet, so we can no longer see them. But given that most of the universe glows in H alpha and almost only in H alpha when excited, we can start thinking that if we imagine that in this particular wavelength, we can see something interesting, and we are not interested in anything else. Or rather, we are interested in other things that are found in interstellar medium that are star stuff. So they are the heavier atoms that are produced inside stars. So I put here a table from Wikipedia that is the relative abundance of the most common elements found in the Milky Way. So hydrogen is by far the most common element, followed by helium, then oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, and sulfur, and then trace amount of everything else all the way to the heavier atoms, of course. Anything that we found, anything heavy, so to speak, that we found on Earth, like gold, like uranium, was actually produced at some point in a supernova explosion. So if we want to look at other chemical species, we maybe want to focus on something that is interesting from a stellar evolution standpoint. For instance, I mentioned that planetary nebulae are rich in oxygen. So if you want to study the evolution of giant stars when they shed the outer layers they become a planetary nebula, probably you want to image in the light of a twice ionized oxygen. If you want to study supernovae, ionized sulfur could be a good idea because it highlights really well the region of the interstellar media that are compressed by the shock wave from the supernova. And so this hydrogen, oxygen, and sulfur forms the triad that most amateur astronomers do narrowband imaging in. We don't do it to study, of course, we don't do science here. We do it because they are, essentially because we copied what Hubble did. The Hubble Space Telescope used these 3 filters, and all the images that they popularized are rendered in a color palette that we call the Hubble palette. But there are reasons for why professional astronomers do that, and we imitate them, to be honest. So it is good we said that we are only interested in those few wavelengths, but why do I need to use a narrowband technique for that? Can I just use a color camera? After all, a color camera captures all wavelengths, which should include also those wavelengths. And it's true, we can do that, but compared to broadband imaging, using narrowband filters has three main advantages. It's much more selective and gives you much higher contrast. It reduces the presence of the stars. And most importantly for us, it greatly reduces the effect of light pollution. And I'm going to show you how. So first of all, why does it improve the contrast? Why does it improve the detail? Why does it decrease the presence of stars? Well, because you are isolating one particular wavelength. It means that you're only going to image those structures of the interstellar media that emit that particular wavelength. And everything else would be essentially black. So the details and the edges become very crisp. Also, stars are what I call black body radiators. So they emit light in a continuum. If you cut away 90% of that continuum, you're also cutting away 90% of the light of the star. And the stars can be, let's say, obtrusive in an image. An example here. So these are 2 pictures of the very same detail of the same object. The Pac-Man Nebula, which we're going to see in greater detail later. They were taken with the same telescope, but with different cameras. So with a color camera here, and the monochromatic camera with narrowband filters on the right. You see how the stars are almost invisible in the narrowband image, but most importantly, you see how all those faint and the thin filaments in the dark portion of the nebula are visible, whereas they are entirely blurred in the color image, almost invisible. Yeah, you can see that the shape is roughly the same, but none of the detail comes through. Another example here. This is a nebula called the Tadpole Nebula. The tadpoles are actually those 2 structures that are visible in the narrowband image on the right as those 2 columns of light that seem to protrude in the center of the nebula. They are barely visible in the color image. They are very visible in the narrowband version. And again, the stars almost disappear. Yes?
Do you get a spectrum of colors out of a narrowband filter?
Yes, you do. And I have one slide exactly on that to show you. Yep.
Indulge me for a second. Which?
Oh, sure. Sorry. So this was taken with a color camera, the image on the left. The image on the right was taken with a monochromatic camera and the narrowband filters. 3 types of the 3 filters that I mentioned, oxygen, hydrogen, and sulfur. And on the topic of star presence, look at the difference here. Same object, the Wizard Nebula, on the left, taken with a color camera. It's actually a DSLR camera. On the right, taken with a monochromatic camera and 3 narrowband filters. The object is the same, but it's almost invisible because there are too many stars on the left. And the detail is completely, there's almost no comparison. But in addition to this, the real game changer for urban imagers like me is the reduced impact of light pollution in narrowband. Why is that? Well, it's because light pollution, especially nowadays that every city has transitioned to LED lighting, is a very much broadband. So you find the spectrum covers everything from violet to red. But warm ISM's light only happens in discrete, very well separated wavelengths. So if only I had a filter that lets that blocks the light pollution, but lets the light from my object pass. But that's exactly what a narrowband filter does. If I have an object that is mostly made of hydrogen, and I image it with a filter tuned to the light of the hydrogen, I'm going to capture maybe 90% of the light of the object. These filters are not perfect, but I'm going to reject 90% of the light that I don't want from light pollution. So I am tipping the scales in my favor by a factor of 10 if I do that. It doesn't work for all targets, unfortunately. It works perfectly well for emission nebulae, so the warm portion of the ISM. It doesn't work for dust, for reflection nebula, everything which is cold and doesn't glow of its own. If you recall the simulation that we did, now let's assume that the background is a broadband reflector, and the center target is only emitting in hydrogen light, and I image it with a narrowband filter. This is what I'm going to get. My camera is going to see a very dark background, but the object is almost unaltered, and so the signal to noise ratio is super high. It's very well visible. This is why we do this. And now I come to the question about colors. So how about colors? So the 3 spectral lines that we are using, as I said, that they are hydrogen, oxygen, and sulfur. In terms of wavelength, sulfur has a wavelength of 672 nanometers. H alpha has a wavelength of 656 nanometers, and O3 has a wavelength of 501 nanometers. So this can be a problem because sulfur and hydrogen are very close to one another, only 16 nanometers of spread. If I plot the color space that I would span, if I create a picture with these 3 wavelengths, and that's the chart on the right, this color space is essentially just a line. It's actually a very skinny triangle. It means that my image can only contain reds and greens. It will not be a very attractive image, in other words. So because of this, instead of doing that, we arbitrarily decided to assign each of the wavelengths to one of the 3 primaries in the red, green, and blue triad. We are doing what is called tone mapping or color mapping. So we create our own color palette. We are not using, it's not natural, it's no longer natural, these are false colors. But in doing so, we can span a much larger color space, make accessible to the eye the difference between sulfur and hydrogen that wouldn't be distinguishable from one another. And we create, in doing so, also an image that is more pleasing to the eye. And the interesting thing is that the choice of the primaries, or even a combination of the primaries, is arbitrary. So you can create multiple color palettes for the same object. An example here, this is called the bubble nebula, and this is rendered in a palette that you can consider roughly natural, in which blue corresponds to oxygen and red corresponds to hydrogen. If I choose to render this in the Hubble palette, I get this. It's the same information. It's just rendered in a different way. So it gives us additional degree of freedom in creating essentially art, not and going beyond the actual color. Yes. Yep. Yep. Yeah. 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 I mean, it's the reason why, as I said, we're probably imitating professional astronomers. We are imitating what the Hubble Space Telescope is doing. The Hubble Space Telescope chose sulfur 2, even though it's very close to hydrogen alpha, because it's a marker of supernova activity. So it's interesting from an astrophysics perspective. For us, it's not that interesting we are not astrophysicists, but it's if we follow the same rules and we assign sulfur to red, hydrogen to green, and oxygen to blue, we obtain an image in the Hubble palette, which is pleasing to the eye. Yes?
So is this done by taking, for example, a monochromatic detector, basically put a first filter, store that image, then a second filter, store that image,
Yeah.
third filter, and then the reconstruction happens?
That's exactly it. So what I have here, one of the telescopes that I'm using, what I haven't brought, I apologize, is the camera. The camera is actually just a detector, a CMOS detector with a cooler attached to it to cut down the thermal noise. And in front of it is a filter wheel. So I have 7 positions, 7 filters mounted in this wheel, and there's a stepper motor that moves the filter that I want in front of the sensor. The sensor is not sensitive to colors. It's equally sensitive to everything, and the filter selects what the sensor sees.
What is the bubble in the middle?
Yes. So there's at the center, the bubble is essentially a shock wave that a central star is creating on the interstellar medium around it. So this star is very hot. It emits a very strong stellar wind. The stellar wind meets the interstellar medium, the hydrogen and oxygen atoms that surround the star, and because of the compression, creates this visible bubble. It's a shock wave, essentially.
You were out in far space and took a picture of the solar system. Would you get that kind of an image?
No, our sun is a very boring star. It's right in the middle of the main sequence, so it's not. This is a super hot star, like 400,000 degrees. So it's, yeah. Yes.
So, great presentation. Thank you.
Thank you.
What happens if you put a color CMOS camera?
Next, I have a slide on that. All right. So, oh, the scale. So this one is about, I think this is about 6,000 light years away, which means that each pixel, I mean, every 15 pixels in this image is 1 light year. So the scale is huge.
Which picture is which?
This one is just the data is the same, it's just rendered in different ways. Yeah.
And many CMOS detectors become really, really low in price.
Yeah.
As opposed to like your CCDs. That
Yep.
The cooling's expensive. So the reason to cool the CMOS is just long exposures.
It's to make it predictable, the contribution of thermal signal. So you can actually remove the signal and you only remain with noise. Noise, we have to accept it. But yeah, make it predictable the amount of signal that you're going to get from thermal signal. Yep. Right, so that's the topic that you were starting to touch, how to capture narrowband data. So the traditional way is with the monochromatic camera or a panchromatic camera and a set of narrowband filters like the magic triad, the sulfur, hydrogen, and oxygen. More recently, we had somebody that wants to enter. More recently, there's been a number of multi-narrowband filters that have hit the market. The first one to appear, I think it was the Radian Triad. So these are interesting ideas. The idea is to use with a one-shot color camera, so a color camera, or a DSLR, and this filter will transmit at the same time, not just hydrogen or just oxygen, but a few, three in the case of the Triad, the filter, 3 wavelengths at the same time. And the position of this of the 3 windows of transmission is calibrated in such a way that each of the 3 pixels, each of the 3 colors of the Bayer matrix will receive some signals. And so you will be able, you don't throw away data from your color sensor, but you will be able to recreate your image in a slightly different way, because of course, then you have to separate the 3 colors and produce, create your own false color palette. And these filters have been have become very popular. Unfortunately, they're also quite expensive, but everything is.
You get more resolution.
Yeah, because you only have 1 pixel each 4, or 2 in the case of green, but one red and 1 blue every cell of 4 pixels. So yeah, it's that's the compromise. But of course, you cut the exposure time significantly. So these are some examples of manufacturers of narrowband filters. These are for filters with individual transmission windows. So there's only oxygen, only hydrogen, etc. And these are examples of the transmission windows of some multi-narrowband filters. As you can see, this is the IDAS NB1. It transmits essentially oxygen, 501 nanometers, and hydrogen. The Triad actually transmits 4, sorry, that's the Triad Ultra. It has 4 transmission windows centered around hydrogen, sulfur, oxygen 3, and hydrogen beta, which is another spectral line of the hydrogen spectrum. And this is yet another manufacturer, Optolong. Whatever filter you use, there is one drawback to how effectively narrowband filters cut down background signal. The magnitude of the photon noise goes down significantly, and it becomes similar to the magnitude of the camera inherent noise, what we call the readout noise. Now, with the CCD cameras, this was a real problem because the CCD cameras used to have a very high readout noise. Each pixel could be affected by a noise in the order of 20 electrons. CMOS cameras have much less of this problem because the noise is very low, could be less than 2 electrons per pixel. But in any case, there are some controls that we have over this process. We could, for instance, decrease the read noise typically by increasing the gain setting of the camera. But be careful, because if you do so, you also decrease the well capacity, the maximum numbers of electrons that can be stored in each pixel. And so you're reducing the dynamic range. And dynamic range is never enough in astrophotography. Or you have to increase the photon noise by increasing the signal, or i.e. increasing the exposure time. When I image from home, 5 minutes are enough with a CMOS camera. If I had a CCD camera, probably 20 minutes would even not be enough to swamp my readout noise. So this is an example of the noise, the read noise curve of a commercial camera. And as you can see, there is a critical value of gain in which something happens in the electronics, and the noise drops from 3 electrons per pixel to less than half, one and a half. But as you can see here, FW means full well capacity. Full well capacity goes down, obviously. And that's what I was saying. With all the CCD cameras, narrowband used to require very long sub-exposures. Nowadays, with low noise CMOS cameras, 5 minutes are sufficient, even to image from, I mean, if you're imaging from a high Bortle area, so areas that have a high Bortle rating, like, unfortunately, the one we live in. It's Mountain View is Bortle 7, San Jose can be up to Bortle 9. Pinnacles in comparison is Bortle 3. Just a very few words about, final words about image processing. As I said, there are things that you have to do after you collect data. You have to reconstruct the image and build your own color palette. This is what we call image processing. And it is a huge subject in itself. I can even adjust an entire presentation for this would not be sufficient. There are books and books on this. But in general, images need to be calibrated, stacked together, and then post-processed. And post-processing has topics like deconvolution, noise reduction, color calibration, high dynamic range rendering. Each of these would probably require a treatise of its own. Additionally, narrowband images require you to choose a palette, and you may spend a significant time trying different palettes and see which is the one that is most pleasing for your object. And you do this with a specialized software, typically not just with Adobe Photoshop. That can be used, but there are tools that are more specialized for that, like PixInsight, like Star Tools, or AstroPixel Processor. Although I cannot tonight go much deeper in this topic, I want to give you a few pointers if you're interested in this. These are excellent websites that cover a broad range of topics related to astrophotography, to processing. In particular, let me point out Rogelio's website. Rogelio is a local imager. He lives in Sunnyvale. Rogelio Bernal Andreo, yeah, deepskycolors.com. He is a local imager that has done groundbreaking work on a very wide field mosaics with incredible colors. That's, I mean, this. I think that the punchline in his website is the night sky is anything but black. And to remain in this topic, I would like to show you a little gallery. We have the time? All right, so I'll start with this, which is the combination of the North American Nebula and the Pelican Nebula in the constellation Cygnus in the summer Milky Way. I imaged this last year from home. This is a portion of a large supernova remnant in Cygnus. So what we are seeing here is the shock wave that is still expanding in space from a star that exploded 20,000 years ago. And this is the full view of one of the details that we saw in one of the previous slides. This is the Pac-Man Nebula. You can see why it's called Pac-Man, the shape. Narrowband images can also be rendered as black and white images if you are so inclined. So this is only the hydrogen signal from the Pelican Nebula. And this is only the hydrogen signal from the Wizard Nebula. This is I call it the heart of the heart. This is called the Heart Nebula, and this is the very core of the Heart Nebula. This is all narrowband. The tadpoles, we already saw this one. This is another, this is called the Crescent Nebula in Cygnus. It's a shell of gas around a Wolf-Rayet star, so it's a very hot star. This is the bubble where the stellar wind impacts the interstellar medium and creates this visible shock wave. Lowers Nebula in Orion, imaged last winter. This is it's called the Thor's helmet in Monoceros. It's like the Norse god, a hero that wears a helmet with two wings. Yes, this is also a shockwave, a bubble. It's a Wolf-Rayet star. Narrowband imaging can also be used to supplement broadband imaging. So this is a star field in Cygnus. I imaged the stars using red, green, and blue filters. So it's a full color image from the dark sky at Pinnacles. And then I started adding hydrogen data collected from home. So I try to make the best of the opportunity of being under a dark sky to image a broadband target. And then from home, I added the narrowband data. Narrowband data can also be used for, actually can be used for science, that's not what I do, but you see that blue arc in the right portion of the star. That's actually the shock wave created by the Cygnus X1 X-ray source. So this is a star that orbits a black hole, and it orbits so fast that goes around in 8 days. And it's the black hole actually emits a relativistic jet of particles that impacting the interstellar medium create that visible shock wave. And just by coincidence, sits next to a very beautiful object, which is this colorful nebula called the Tulip Nebula. This is my own version of the pillars of creation. Of course, much lower resolution than Hubble. This is the view of the Omega Nebula in, I think it's in Serpent, not in Sagittarius. Yep. Let me go back.
How many pixels are we looking at?
Oh, so my camera is not super high resolution. It's 11 megapixels. So it's about 4,000 by 3,000. There are cameras nowadays that have 20, 40 megapixels. And it's one of the problems of astro imaging and then processing is the amount of storage space that this takes. In one night of imaging, I probably have a couple of gigabytes. This quickly adds up, so you can find yourself with 1 terabyte of data collected in 1 year. This is Sharpless 86. It's I imaged this object first in broadband, and it's almost nothing. It's yeah, you can see some red glow, but those nice pillars of dust are almost invisible. So the dust itself does not emit narrowband light. It's actually black, but it's the contrast that makes it visible. It's the fact that it projects against a narrowband suitable background. This is the full view of the supernova remnant in Cygnus that we saw at the very beginning. This is a mosaic of 4 different panels taken with that telescope. So with a small 65 millimeter refractor telescope, sorry. Again, a combination of broadband stars and the narrowband hydrogen signal. This is called the Spaghetti Nebula. This is the Lion Nebula. And this is a region visible in the winter Milky Way. It's called the Christmas tree or the Cone Nebula. This is rendered in the, not in my usual palette, but it's rendered with the Hubble palette. This, some people call this the eye in the sky. It's the Wolf-Rayet 134 star and the surrounding nebula. So the star itself is has a temperature of about 60,000 Kelvin degrees, but because it's so hot, it's the star itself is only 5 times more massive than the sun, but because it's so hot, its luminosity is 400,000 times the luminosity of the sun. Most of its radiation is in the far ultraviolet or X-ray, and so it ionizes a shell of gas around it, creating this nice blue bubble, which is essentially oxygen. This is called the Squid Nebula, and the squid itself only glows in oxygen light. It's basically invisible in broadband, and even in narrowband, it took me 40 hours of exposure to get this image. And I believe this is my last image. This is an object that's really beautiful in the Hubble palette. This is the Seagull Nebula. It's nice that it has all these greens and the gold and the blue, not just red. Antonio, you were saying something? Oh, I'm so sorry.
You mentioned a couple of times, just said 40 hours.
Yeah.
You mentioned 20 hours before. So that's multiple nights.
Of course, yeah.
So how are you?
So the huge advantage
How
of
are you
it,
doing that?
the huge advantage of imaging from the backyard is that you can image night after night using automation, using programs that automate your collection. So there's a program in which you can program your sequence of objects that says, yeah, move, wait for the object to clear the trees, then point there and start taking pictures, 10 minutes in each filter, and repeat until the object has crossed the meridian and starts going down behind the trees on the other side of the backyard. You do this night after night. In 1 week, you can capture 30 hours. And all the pictures that you've seen in this last gallery, they were all collected from the backyard here in Mountain View.
On our side of the galaxy.
They are all present, all in our galaxy, yes. You can image other galaxies, of course.
No, but even not within the galaxy.
Oh, in our arm, most of them are so the ones in the summer Milky Way are in the Perseus arm or in the Cygnus arm, and in the winter we get those from the Monoceros arm, which is slightly farther away. And so an object like this one, I think I have this is 3,500 light years away, whereas an object like, oh, sorry. This one, we're getting there. Yeah, this one is 2,400 light years away. So it's about 2/3 of the distance of the other one. The winter objects are typically closer than the ones in the winter because of the difference between the two spiral arms. Yeah. Everything here is within our galaxy. We are only, you can image other galaxies, but typically not in narrowband because galaxies are broadband targets. And so you want to capture them when you are under a dark sky. Yes.
Two questions. Okay, so correct me if I'm wrong, but I cannot use narrowband filters, for example, for exoplanet detection.
Right.
That's second, you mentioned here about LED lights being that kind of white.
Yeah.
But you don't have to agree with the city sounds that only use gas lights, not like what is it, sodium light. Yeah.
Yeah.
We don't have any more.
So, yeah, absolutely. I think that they had an agreement with the Lick Observatory to do that. I have a feeling that Lick does not care that much anymore because they are not doing that kind of research anymore. I have a friend of mine actually lives in South San Jose, Borto 9, and he has a spectroscope. And so he took a spectrum of the night sky, and yes, you can see the sodium doublet, but unfortunately, there's also this huge peak around the 400 nanometer, 450 nanometers, that is the primary of the white LEDs, and then it's the white LEDs re-emit in almost all the rest of the spectrum. Yeah. Yes.
There should be a way to actually have public lighting to have at least,
Which is more astronomy friendly. I would be happy enough if at least they didn't do this. This is Cuesta Park. So the trees are illuminated, which means that light goes in the sky.
There's multiple cities.
no, exactly. I just say it's a public service.
Let me also try people on Zoom. If you guys have any questions, please unmute yourself.
Yep.
But not all speak at once. Feel free or raise your hand. We'll try and get to. Oh, go ahead. Continue.
Yes.
So, you mentioned cold, warm, and hot.
So, you mentioned the triangle filter, and the two of the colors are
Right.
distinguishable. Do you have any, do you have any images that show using one of those triad filters, some sort of natural, color image that are mostly two-color?
Good question. I don't have any image myself because I don't have one of those filters. I've seen, so if you just take your image as it comes out to the camera, you're probably going to get something similar to this. Yeah, this is the two color. This is only hydrogen and oxygen. So you're probably going to get something similar to this. And yeah, it's beautiful. But it's not really a full color image because you need at least 3 primaries to produce to have a wide color space.
And would you get something remotely like this with the naked eye, or does it require?
This is a relatively bright object. You can see it in a telescope from a dark sky, not from home, nothing at all. From pinnacles, for instance, especially using visual filters. There are narrowband filters that you can use for visual observation. You see this. What you don't see are the colors because our eyes don't really respond well to colors at night. And you see some of the brighter filaments, but you don't see the fainter portions like this. Yes.
So even at pinnacles, you use narrowband filters just to knock down the star.
I normally don't do that, but just because I try to make the best of the opportunity of being at pinnacles under a dark sky. And so I prefer to capture the broadband portion at pinnacles and the narrowband from home. Yeah. But yeah, you could. Yes. Yes, it's a pretty good one, and the park rangers are doing a lot to credit themselves as a dark sky sanctuary. They actually do, during the summer, they have public star parties, and people that are camping at Pinnacles East typically attend. I've been to a few of them. It's a very nice place, and the rangers are very, not only they let us image when even outside of star parties, but during the star parties, they are absolutely great. They show the way for the campers. They have set up a number of lanterns that are dim enough not to disturb the astronomers, but pave the way for people to reach us. Very nice.
For the people on the Zoom meeting, if you have any questions, please unmute yourself and speak slowly and clearly. Otherwise, I'll wait 1 minute. But if there's more questions from the audience, I do have a couple of questions for you.
Absolutely.
So do you share this with professional astronomers?
So these type of images are probably not interesting to professional astronomers because they are mostly for mostly what we call pretty pictures. They don't have scientific value. But I've been in contact with professional astronomers for other things that I'm doing, like last month, no, sorry, 2 months ago, a supernova exploded in the M101 galaxy in Ursa Major, and almost every clear night, I took a few images of that galaxy, not in narrowband, not to make a pretty picture, but to do photometry. So I measured the brightness of that star, and I shared it with an astrophysicist in Canada, and yeah, they are using them to build the light curve. I have actually a picture of that. I can show you. Okay, how do I do this? Like this. So this is the galaxy that the host galaxy M101. The supernova is here. This one. This star here. And so this it's not impossible to take pictures of galaxies from light pollution. This was taken from the backyard, but it takes many hours. And it will never be as good as you could do in just one night from a dark site. So this is why people who are really into this, they move their telescopes to a place like New Mexico or even the Atacama Desert. There are essentially services that host your telescope connected to the internet, and you dial into your telescope remotely.
And the other thing I'm actually quite fascinated, another beautiful objects of art in themselves, but when people look at stars, they don't realize all the gas that's there, that's available for more stars.
Yeah.
Your images, I think, highlight that.
Yeah, it's in particular when we look at other galaxies, these regions here, the glow in these are what's called the H2 region. H2 means ionized hydrogen. These are where new stars will form. These are becoming hotter and hotter, and at some point, under the influence of gravity, the pressure will be enough that the nuclear fusion will ignite, and this will become a star. Or in this case, this is the end of a star, it's the supernova.
So I'm going to shut down the Zoom.
Yep.
But in the audience, you're quite welcome to remain. So to kick us out tonight, that's when we're very essential. So thank you very much.
Thank you very much for having me.